have seen before. And then an important relation, of course, is how we back engineer the field if we were to know the potential. We've shown how to obtain the potential from the field, namely by performing the line integral. However, this operation, of course, has an inverse, which is computing the field from the potential. And here we're just using essentially a tautological approach, because by definition, we know that, the fundamental theorem of calculus, if I write the integral of the differential of a function, then I get the function evaluated at the two endpoints. Okay, and in the case of a line integral, this is precisely the definition of the gradient of the function, if you want. Okay, so this is just using the definition of the gradient in there. Therefore, when I compare this left-hand side here, expressed in terms of the definition of the gradient of phi, to the earlier expression that we had, namely that this is minus the line integral of the electrical field, then I get an equation of integral form between the integral of the gradient of phi and the integral of the field. Okay. However, because this relationship holds for arbitrarily chosen endpoints of the integrals, it has to be true at the level of the integrand itself, locally. Okay. Therefore, grad phi has to be minus E, or said otherwise, E has to be minus grad phi. Okay, so that's the magical little relationship here. And if you are worried about it, you can do an explicit check for the case of point charge distributions, because we had an earlier expression for the electrostatic field coming from a series of point charges. This was this, R over R cubed expression here. And you can obtain indeed the correspondence here by simply observing that R vector over R cubed is just minus the gradient of the scalar 1 over R minus R prime. Okay, so this is just a mathematical identity. Okay, so here, of course, in this equation E minus grad phi, you have a space coordinate as argument for the electrostatic field, and of course also for the scalar potential, for the electrostatic potential. So this is an equation that holds at all individual points in space. Okay, and again, I kind of hope you're all happy with this. Okay, so you're all happy with this, right? I mean, yes, very good, very good. Okay, so basic concepts. However, the kind of profundity of these concepts, perhaps, is slowly dawning on you, right? So it looks very, very simple at first, but it's actually extremely profound that all these things hold. Okay, and here again, we can do countless examples. There are 2 of them in the notes, one of which I will do here, the second of which I will comment on very briefly. Example, we have a uniformly charged spherical shell. When we use the word shell, we mean infinitely thin little, like not even egg-like thing, spherical layer somewhere that contains total charge Q. And that's got radius big I here. Okay, so it's uniformly charged. Therefore, the surface charge density of that thing is just the total charge divided by the area of that sphere, 4 pi r squared. And we can use, so we want to compute the potential, and we're going to compute the potential by just computing first the field and then doing our integrals. So we have seen Gauss's law. Gauss's law, we have learned, is really applicable in highly symmetric situations. Well, you can't really ask for much more symmetric situation than this one, completely spherically rotational symmetric. Only dependence is on the radius. And therefore, if I use the logic of Gauss's law, I say, okay, I'm going to englobe my spherical shell with another kind of spherical integral shell around it, at a radius little r, and now I'm going to use the fact that the thing is completely rotationally invariant. Therefore, the only direction for the electrostatic field that is compatible with this is purely radial. Okay? Field is purely radial, therefore, when I do the integral over this Gaussian surface at radius little r bigger than r, encompassing my my shell, I just get 4 pi little r squared times the value of the field. And then I just know that this is Q enclosed over epsilon 0, and therefore the electrostatic field coming from this uniformly charged shell is just Q over 4 pi epsilon 0 in the radial direction r hat, falling like 1 over r squared if little r is bigger than the radius of the shell. Conversely, if the radius of my Gaussian shell for integration is lower than the radius of the charged shell, I do the same integral, except that Q enclosed is suddenly 0. Therefore, the field inside this object is strictly 0. Okay? And proving this, I remind you, was the whole purpose of Cavendish's experiment. Okay? It's an absolutely remarkable fact about these things. And it's true. Okay? So that's our electrostatic field for this simple configuration. And now to compute the potential, once again, we choose a reference point, which is handy. In this case, let's just put it at infinity. And if I want to know the potential at a reference point, r vector here, which is further distant from the origin than the radius of the charged shell, then I can just use the line integral of this electrical field here. Again, for simplicity, put as a line integral in the strictly radial direction, all the way down, well, from infinity, Canada, all the way down to the evaluation point r that you have. And, oh miracle, you just recover exactly the potential from a point charge. Okay? But now with this 1 over r. And if I happen to require the knowledge of the potential at a position which is now inside this charged shell, then I just carry on with my integral. Yeah, I go from infinity to the surface of the shell, and then inside the shell to my evaluation point. But of course, the second bit of the integral, it's kind of simple because the field is 0. So you just go wherever you want inside the shell, and the value of the potential doesn't change. So the potential inside the shell is just this constant, which is the value at the shell. Okay? So that's a simple reasoning with these things. And again, I hope you've done this reasoning in your first course in detail. Am I right, or am I right? Very good. Okay, you can check in the online notes. There is the usual torture example of actually computing the potential from a direct integration of the over the surface of the shell like this. This is an exercise in integration. Again, I'll let you have a look at it. It's nice to be able to do it. Most importantly, it's very nice to be able to recognize when you don't need to do such complicated integrals. Okay, so just have a look at it, and I'm not going to do it here because I don't want to teach you to do complicated integrals when you can just shake the hand of your good friend Gauss and do it almost for free. Okay, so that's the kind of introduction to the thing. So are we all like completely happy and comfortable and friendly with our good friend, the potential? Yes, we're happy. Yeah? Okay. So so now